I'm going to do a quick graphing review of some of the kinds of things that we need to be able to do for dealing with definite integrals in 17b. So the first set of functions that we want to make sure for sure that we can graph are lines. The equation of a line can come in a couple of different forms. The most common form we're used to seeing, we usually just refer to as like y equals mx plus b. So this is something like maybe 2x plus 1. And in this form, that 2 right there, it's telling me the slope, and the 1 is telling me the y-intercept. And absolutely, you can graph this line by thinking about that y-intercept and the slope. So I'm going to get my axes on here, and if the y-intercept is 1, then that means it's going to hit the y-axis at 1. That slope of 2 is telling me to go up 2 and 1 to the right. And then I can connect those dots and continue to go up 2, 1 to the right. The other thing that we can do if we wanted to sketch this line, and in particular, if the only thing we need is a quick sketch so that we can talk about some definite integrals, the other thing that we could do is just plug in 2 points. So let's say that this came up in the context of looking at the definite integral from 3 to 7 of 2x plus 1 dx. Well, in this case, if I had to graph it, the only 2 x values that we're actually concerned about are 3 and 7. So I could take the 3 and plug it into the function. 2 times 3, I get 6, plus 1, I'm at 7. So I'm going to come over here to the point 3, 7. Next up, I care about the 7. So when I plug in 7, 2 times 7 is 14, plus 1, I'm at 15. And I'm going to come over here and I'm going to call that 7. And I'm not going to worry about it being perfect. I'm just going to label this as the point 7, 15 and sketch the straight line between them. Because in the context of definite integrals, I don't need the whole picture. Right now, I just need to know that's the part that we're looking at. Next up, after we talk about lines, next thing that we would talk about is parabolas. In the context of definite integrals, really the 2 important things to note for parabolas are whether it's concave up or concave down, and then how it's shifted. So if I think about something like y equals 4 minus x squared, this is taking our standard, like basic y equals x squared kind of parabola, the minus sign in front of the x squared here, that negative coefficient is telling me that this parabola is concave down. And that 4 out there is telling me that it's shifted up 4. If I go to sketch this, I know that it's a concave down parabola, and we can think about this as shifted up 4. I think it's easier to just find the y-intercept. So finding the y-intercept means plugging in 0 for x. And when we plug in 0, we get 4 for y. So this thing has a y-intercept of 0, 4. Because that's negative, it's concave down. Our parabolas can get more, this one happens to be shifted up down, but we can also have parabolas that are shifted left right. So maybe I had a parabola that looked like y equals 3 plus x squared. If I were trying to sketch this, again, just in the context of I need to do something with it for a definite integral, because I have something in parentheses squared, the thing that I'm going to note is what x value makes the part in the parentheses equal to 0. So if 3 plus x is equal to 0, that means x is equal to negative 3. So this parabola hits the x-axis over here at negative 3. Again, I need to know how it's shifted, and I need to know whether it's concave up or concave down. So to decide if it's concave up or concave down, I need to know the coefficient in front of the x squared. That might mean that we want to multiply this out, which we could. That's going to be 9 plus 6x plus x squared. But I can also look at this and say everything in here is positive, and we're going to go ahead and square it. For sure, this thing is concave up. So I've got my point. I draw my concave up parabola. It doesn't have to be perfect, just has to be good enough so that we have a general sense of what's going on for that definite integral. A couple more functions that I want to bring up: sine, cosine, and exponentials. We will definitely need more with the graphs for exponentials and log functions when we get deeper into talking about antiderivatives and definite integrals. But for now, just a quick recap: y equals e to the x. It's just a function that you're going to want to memorize the shape of. This guy has an intercept, has a y-intercept of 1 because e to the 0 is equal to 1, and has a horizontal asymptote at 0 because as x approaches negative infinity, this function gets closer and closer to 0. So this has a general shape like that, and that's about all we need to know in the context of 17b. For sine and cosine, especially when we're talking about definite integrals in the context of interpreting definite integrals as signed area, that's sine with a GN, it is important that we know really the basic features of cosine and sine. So y equals cosine of x. We often say starts at 1. That really just means that it has a peak here when x equals 0, or we have a peak of 1, and cosine looks like that. Now cosine completes one period or one cycle in 2 pi, but technically keeps going in either direction indefinitely. So for cosine and sine, when we're talking about definite integrals, it's important to know what our bounds are. So if I only wanted to look at cosine of x, for example, on pi over 2 is less than or equal to x is less than or equal to 2 pi, the thing that's important to know about the sine and cosine graphs is kind of where they're hitting. So here, I know that cosine completes one full cycle in 2 pi, so that means that it's at this midpoint at pi, and this right here would be pi over 2. So if I care about cosine on pi over 2 to 2 pi, that means in terms of the graph, I'd be looking at all of this, and additionally all of this. So even though right in this moment, I couldn't tell you the exact value for the definite integral on pi over 2 to 2 pi, I could tell you that it should work out to be negative because there's more area under the curve in that window than there is above the x-axis. Similarly for sine, we talk about starting at 0, but again, sine and cosine both continue in both directions. So it really just is telling us that y equals sine of x does pass through the point 0, 0, but it keeps going in either direction. And similarly to cosine, we want to make sure that we're looking at a particular, if it's a definite integral, we're going to have a particular window we're looking at. So let's say in this case that I actually wanted to look from 0 to 2 pi. Well, again, sine's going to finish one complete cycle in 2 pi. So if I were going from 0 to 2 pi, we'd be looking at all of this and all of this. Well, now we have perfectly matched area above the curve and below the curve. So that tells me that if I did look at the integral from 0 to 2 pi of sine of x dx, this should work out to be 0.